Kevin Allen Dooley Inc. is a technical, research, and invention firm based in Toronto, Ontario, Canada. It was founded in January of 2013 by partners Kevin Dooley and Elwood Morris. The two share a 40-year working relationship at former employer Pratt & Whitney Canada, which is a gas turbine aircraft engine manufacturer. Mr. Dooley spent much of his time in the position of Fellow Emerging Technologies, where he was involved in various technical problem-solving disciplines. During the course of his time there, he received the title of inventor on over 100 issued patents to date, particularly in the fields of electronics, electromagnetics, mechanics, and acoustics. Mr. Elwood Morris was a professional aerospace engineer who was involved in the development of the JT-15D aircraft engine and was a customer liaison to Cessna, Learjet, and Mitsubishi. Kevin Allen Dooley Incorporated was formed after the two partners took up a special interest in some of the unusual health claims being made about infrasound exposure. This initial interest has since led to the publication of two research papers authored by Dooley et al. By the Acoustic Society of America, as well as the development of infrasound production and active suppression technology. Early prototypes have already undergone successful field testing, and beta versions of this system have also been built and successfully tested for performance. The firm is presently working on an automotive pilot study to explore the potential reduction of passenger motion sickness and driver fatigue in automobiles. Today's presentation is titled Infrasound and Motion Sickness, an Overview, where Mr. Dooley discusses what we believe to be the link between infrasound and some forms of motion sickness symptoms in sensitive people.
Motion sickness is most often associated with nausea and vomiting. However, we've been doing quite a bit of research on motion sickness during 2013 and 2014, and I've come to understand that motion sickness, and more specifically a subset of symptoms called Sopite syndrome, is actually what is probably affecting some people in homes near wind turbines. So let's get started on our findings. Motion sickness symptoms, including Sopite syndrome: sleep disturbances, dizziness and nausea, mood changes, drowsiness, apathy, yawning, and disinclination for work. Sopite syndrome is a manifestation of motion sickness that we believe is of particular interest. The accepted theory of the cause of motion sickness is sensory conflict in the central nervous system. Sensory conflict is when two or more of your senses, visual, vestibular or balance and kinesthetic or touch, disagree with each other about your own personal motion. Let's look at some examples. What is shown here is a schematic that represents the three primary sensory systems and the central nervous system or brain. This diagram is indicating what the sensory system may be interpreting while reading in a car. The inner ear and kinesthetic or touch sensory system are receiving motion cues, while the visual system is not. This leads to a sensory conflict, which in some people leads to motion sickness. A similar situation occurs in a cruise ship passenger cabin, where again both the inner ear and touch or kinesthetic sensory systems receive motion cues, but the visual system does not, again leading to what is known as seasickness. In both the car and cruise ship situations, motion sickness can often be remedied by looking at the horizon or out of a window, such to provide a visual motion cue. In the case of a flight simulator and some video games, there are less kinesthetic or vestibular motion cues. However, there are visual motion cues which can also cause a sensory conflict, sometimes leading to motion sickness symptoms. When we go for a walk, all sensory systems are receiving motion cues and are in agreement. Therefore, there is no sensory conflict and all is normal. So how does infrasound fit into all this? Let's first look at what infrasound actually is. All forms of sound are simply rapid fluctuations in the local or surrounding barometric pressure. We perceive very rapid barometric pressure fluctuations as sound if the fluctuations are between about 20 times per second and 20,000 times per second. These are the pressure fluctuations that we can hear, which are called audible frequencies. Infrasound is relatively slow fluctuations in the local barometric pressure, essentially below about 20 times per second. We can't normally hear this because it is below our range of hearing, which is why it's called infrasound. But our eardrums move at least the same amount for infrasound as they do for audible sound pressures, even though we are not conscious of it. Ultrasound, like infrasound, is also inaudible, but exists above the audible range. This is Betty going for a walk. She's in motion. What we have noticed is a previously unrecognized fundamental physical link between motion and cyclic barometric pressure fluctuations, or infrasound. Not motion sickness and infrasound, but motion itself and infrasound. Infrasound, as it turns out, is a key ingredient of motion, and we believe, to those of us who are sensitive to pressure, it is a motion cue, just as visual motion or other sensory indications of motion are motion cues. Humans have been exposed to infrasound when they move since men and women have been walking the earth. It's an integral part of normal motion. As we move upward by a centimeter, the pressure around our head and torso reduces by about 0.12 Pascal. And when we move downwards, the same pressure increases by about 0.12 pascals. There can be no argument or debate about this. It is a physical fact which is easily tested and proven, and is easily calculated as well. To the person who is walking, this fluctuation is infrasound. This cyclic and symmetrical pressure variation as we walk is, to our sensory system, identical to cyclic symmetrical infrasound from any source. Let's look at an example of an alternate source to walking. Let's say that Betty is one of the people who are sensitive to pressure. If Betty is in her home not moving, there are normally no motion cues. As soon as a cyclic infrasound source is introduced, such as a wind turbine for example, a motion cue is introduced to her vestibular system, causing a sensory conflict in Betty's central nervous system, leading her to experience symptoms of motion sickness and Sopite syndrome. Psychology professor Dr. David Nussbaum wrote his 1985 PhD thesis based on his scientifically controlled study of the way that different people respond to the same infrasound exposure. He performed this study because even back in 1985, there was much disagreement among researchers' findings related to the effect of infrasound exposure on people, and this had nothing to do with wind turbines. Some researchers' findings indicated infrasound caused serious problems, while other reports indicated no effect whatsoever. David Nussbaum suspected that some people may be sensitive to infrasound, where others were not sensitive at all. In David's study, involving 80 test subjects, he sat people in a relatively darkened booth, slightly larger than a telephone booth, and exposed them to quite high levels of infrasound for a period of 30 minutes. The study was performed in accordance with the highest scientific standard with an appropriate control group of 20 subjects. Motion was definitely not a part of this study at any time. The results of the study were quite conclusive. After the 30-minute infrasound exposure period, about 15% of his test subjects reported the onset of what David Nussbaum referred to as motion sickness-like symptoms, including dizziness and nausea. This result typically was reported several hours after the actual exposure. And I want to re-emphasize that these subjects were sitting still in a closed environment. They were not moving, however, still displayed varying symptoms of what David called motion sickness-like symptoms. Several other researchers had previously found similar effects in some test subjects. David also mentioned in his paper a report out of Etobicoke, Ontario, from Sir Adam Beck Public School, where 10% of the student population suddenly began showing unexplained signs of dizziness and nausea. The problem was traced to a faulty air circulation fan, which was producing infrasound or barometric pressure fluctuations throughout the school. Perhaps one of the most interesting demonstrations from David's research was that the pressure fluctuation pattern that was proving to be the most problematic for his test subjects was also the most symmetrical or undistorted pressure wave pattern. Dr. Nussbaum actually exposed his test subjects to both symmetrical and non-symmetrical cyclic infrasound. Interestingly, it was only the symmetrical cyclic infrasound that caused nausea and dizziness. I will just mention again that Nussbaum was using levels of infrasound that are much higher than what is present in a home 500 meters from a wind turbine. And his exposure times were only 30 minutes, which is, of course, a very much shorter exposure period than neighbors of wind turbines would be exposed to much lower infrasound levels. Barometric pressure fluctuations can be either symmetrical, relatively undistorted, or highly non-symmetrical, significantly distorted. A symmetrical cyclic pressure fluctuation occurs when the positive and negative pressure values are equal from the mean value. Here's an example. A non-symmetrical pressure fluctuation occurs when the positive and negative pressure values are unequal from the mean value. Some researchers had previously reported that if the infrasound included distorted pressure patterns, the familiar motion sickness effect on people was minimized, where if the pressure pattern was more purely symmetrical, the negative effects were more often observed. These researchers include Evans and Tempest, 1972, Bryan, 1976, Okai et al., 1980. David retested his sensitive subjects a number of times and included testing with a distorted, now known to have been non-symmetrical, pressure pattern. As you can see from the trace of the pressure wave used by Nussbaum, the positive value of pressure of 89 pascals is offset from the negative value of minus 56 pascals, and as such is non-symmetrical. This pressure pattern is dissimilar to cyclic pressure patterns related to motion and is therefore not likely to be interpreted as a motion cue by the central nervous system. When his sensitive test subjects were exposed to this non-symmetrical pressure pattern, no motion sickness-like symptoms were reported. Nussbaum then re-exposed his sensitive subjects to a symmetrical, undistorted pressure pattern, which is shown here on the screen. Notice the positive and negative pressure values are both the same at about plus 96 and minus 96 pascals. So the pattern is symmetrical and thus similar to a motion-related pressure pattern. It is more likely to be interpreted as a motion cue by the central nervous system than a non-symmetrical pattern. An undistorted or symmetrical pattern was again used to confirm that the sensitive test subjects were in fact still just as sensitive as they had been. This testing confirmed the findings of the previous researchers, but also proved very conclusively that some people were sensitive to infrasound and others were not. Fatigue and lethargy were more commonly observed for the non-symmetrical or distorted pressure patterns, and as a relatively immediate observation rather than a delayed result. We think this effect may be valuable in explaining why certain types of infrasound cause motion sickness symptoms in some sensitive people, and other types of infrasound do not cause problems even for sensitive people. Here are some environments where more symmetrical cyclic infrasound is found. Cruise ships, due to the up and down cyclic motion, cars, and other transport environments have multiple broadband frequency infrasound, which is also symmetrical. Air travel, due to altitude variations in rough weather. Wind turbine infrasound inside the home is often more symmetrical than wind turbine infrasound outside the home because of building filtering effect, and also the tendency for the home's structural responses to the infrasound pulse outside the home. Note that in all of these environments, sensitive people may experience motion sickness symptoms. In cruise ships, cars, and planes, these symptoms occur when your eyes aren't receiving a motion cue, but your inner ears are, which, as we discussed earlier, is what defines a sensory conflict. Inside a home near a wind turbine, we suspect the same thing may be occurring. These are pressure fluctuation patterns recorded by Andy Metelka in a home at roughly 500 meters from a 1.6 megawatt turbine, which have been converted from spectral data to time functions. The green trace is the symmetrical pressure fluctuation present in virtually all modes of transportation where people experience motion sickness. The blue trace is the pressure fluctuation recorded inside the home, and the red trace is the pressure fluctuation recorded outside the home. Notice that the blue trace is much closer to being symmetrical than the red trace. When you're in your home near a wind turbine, your eyes likely are not receiving a motion cue, but depending on your sensitivity, your ears may be receiving a motion cue. The result, of course, would be a sensory conflict leading to Sopite syndrome or motion sickness symptoms. This is an infrasound recording from Norma and Ron Schmidt's house in Underwood, Ontario. Their house is 500 meters from a 1.6 megawatt turbine, and there are many other turbines in the vicinity. The traces represent the variation in barometric pressure in an upstairs bedroom and in the downstairs kitchen area of the home. Notice, once again, the fundamental sine wave pattern forming as the barometric pressure in the home fluctuates up and down on the screen, at the same frequency as the blade passing frequency of the turbine. In this recording, we have filtered the pressure such to identify only the fundamental of the blade pass. This process tends to force the pressure to perhaps appear more symmetrical than it actually is. However, this recording clearly demonstrates that the barometric pressure in the home is varying in a cyclic way similar to what would be experienced while walking. The actual pressure fluctuation indicated here is perhaps slightly higher than may be experienced by the majority of people while walking, and at times is above plus minus 0.15 Pascal. The calibration on the oscilloscope is 0.1 Pascal per centimeter. We are very confident that all forms of smooth natural motion results in symmetrical cyclic pressure fluctuations very similar to the pattern shown here. For perhaps millions of years, the brain has become used to this symmetrical pattern of infrasonic pressure fluctuations from walking. So, what about non-symmetrical or distorted infrasound? There are two basic types of non-symmetrical infrasound: cyclic infrasound and non-cyclic infrasound. Non-cyclic infrasound is very common in our natural environments. It's totally random. Here are some examples: blowing leaves, wind, and crashing waves. The infrasonic pressure fluctuations from these natural sources are non-cyclic and totally random. Some examples of cyclic non-symmetrical infrasound are generated by sources such as the human heart and some wind turbines outside the home. These examples are much less symmetrical than that found in most motion-related environments, and as a result will almost certainly not be interpreted as a motion cue by our central nervous system. This may also be why some infrasound sources commonly used as examples to argue that infrasound is all around us and is thus never hazardous may be incorrect. Some of these examples commonly used in this argument are blowing leaves, crashing waves, and wind in general, which we have just shown are totally random. Homes near to a wind turbine act as a filter, causing the pressure fluctuations inside the home to become more symmetrical than they are outside. We think this could be why people who are sensitive to pressure fluctuations that live near wind turbines are sometimes much more comfortable sleeping outside in tents or barns than sleeping inside their home. So to summarize, the more symmetrical the fluctuation pattern is, the closer it is to a motion cue. The less symmetrical or non-cyclical the fluctuation pattern is, the further away it is from appearing as a motion cue. If it is not cyclical, it is not a motion cue, period, and it should be clear to see why it is not. We are presently wrapping up the development of an infrasound source that can be used for research into infrasound effects. It's our objective over the coming months to make equipment available for purchase by research institutions, which has the ability to simulate any type of infrasound in controlled environments, i.e. in a lab, a home, or in a clinical setting. The same technology forms the basis of a system that can actively suppress wind turbine infrasound in homes that need it. This will suppress the infrasound inside the affected home, removing the motion cue, restoring the central nervous system from a sensory conflicted state to a normal state. We believe that this equipment could be provided to people who are affected by wind turbine infrasound in their homes.